We have come to the last video on the dynamical systems playlist where I get to talk about conceptual synthesis of dynamical systems. So it's like bringing together everything we have learned so far and, to also, show you a kind of way forward as far as dynamical systems are concerned in case you get to do something in this area. Okay, except something comes up. This is the last video here. So straight up to the conceptual synthesis of dynamical systems, this lesson presents a systematic overview of dynamical systems, including determinism versus predictability. These are things we've come across, structure versus randomness, universality in dynamics, open problems, learning pathways with worked examples and Python illustrations like we always do. Okay, so straight up, we have what a dynamical system is about. Of course, a dynamical system describes how a system evolves in time according to fixed rules. So we can have a continuous time system where we have a differential equation representing a dx dt equals f of x. And we can also have a discrete time system where we have this kind of expression x sub n plus 1 equals f into x sub n, where x is the state of the system and f is the evolution rule. In both cases, by the way, then you have types of systems. You can have a linear system, which is an example is a harmonic oscillator. Then you can have a non-linear system, like the predator-prey system. You can have a deterministic system like the Newtonian motion, and then we have stochastic system like stock prices and chaotic system like the weather. Talking about ideas like butterfly effect. You have a butterfly flapping its wings in one place, and then it leads to a tornado in another part of the world. That's the kind of thing we have, the like some very chaotic situation. Okay, so then we talk about determinism versus predictability. So a system is deterministic if its future is completely determined by its present. So that is deterministic. So it means that you can predict the future based on the present, but that's determinism. So example is this the logistic map which we have looked at in almost every video under this playlist, right? X sub n plus 1 equals r x sub n into 1 minus x sub n. And there's no randomness, but things can get chaotic. Then that leads us to the idea of predictability. A deterministic system may still be unpredictable if small errors grow rapidly. We saw that under this map for a particular, like maybe for values of R from 3.87 upwards, it becomes chaotic. This is called sensitive dependence on initial conditions. And this phenomenon is known as chaos. Okay. So if a system is sensitive to initial condition, it leads to chaos for sure. And then we have this example of logistic map. So you have the equation x sub n plus 1 equals this. For r equals 4, the system becomes chaotic. We compare two close initial conditions. Imagine the Python code right here, looking at that. So you define the logistic map r, comma x naught, comma n, where x is equal to x naught for the value. So for everything in the range, we have x is rx into 1 minus x. So you have values that append x. So return values. You have X1, the logistic map, for so because we are taking R to be 4, because the parameters are R, X naught, and N, right? So our R is 4 in each case. But look at this initial condition, 0.4, and this is 0.4001. So just a difference of 0.0001. Very tiny, but see the kind of issue it's going to lead to because the system is sensitive dependence. It is sensitive to the initial condition. Okay, so see that. So you can see that tiny difference in initial condition leading to this kind of difference. So that means the system is chaotic, right? So in summary here, we see that so determinism is rule-based, but and it is sometimes predictable. Then for long-time forecast, right? Determinism is not necessarily good for long-time forecast. Uh, although predictability is often possible like that. So we can say even deterministic systems can be unpredictable. That's the idea here. So even deterministic systems can be unpredictable, right? So then we talk about structure and randomness. Structure and randomness is another concept we talk about in dynamical systems. Okay, so imagine chaotic systems may contain fixed points, that's equilibrium point in a matter of speaking, or what okay, and then you have periodic orbits or attractors or even fractals. Like we said, fractals are complex systems that are built based on very simple systems that are repeated many times, infinitely also. Then you have despite irregularity, patterns can still exist. A very good example is in take a case of fractals or even some periodic orbits. Then we have randomness. Random systems involve noise. Like you have x sub n plus 1 equals f of x n plus n sub n, eta sub n, where eta sub n is the noise. So you can have random systems and what makes a system random is because of noise. Okay. So it's more like when you look at music that is soothing to the ears and music that is not soothing to the ears, it's because you have some noise in there. There's no pattern, there's chaos, maybe if you like. So chaos versus randomness now. So chaos is rule-based, but randomness is not. Chaos is repeatable, but randomness is not. Chaos is long has a long-term structure, but randomness has no long-term structure because it's just random. It's stochastic as you can another that's another word for randomness, right? It's stochastic. You cannot really say what's going to happen next. So chaos looks random but follows rules. So chaos, like in one video we saw that chaos is predictability. No, chaos is determinism plus unpredictability. Okay, so the fact that it is chaotic does not mean that it does not follow rules. It still follow rules despite the fact that it is chaotic. Okay, so we have chaos versus noise, a very good example right here. Imagine, okay, I guess I need to show this in bits and pieces. So imagine this, we using NumPy and Matplotlib now, we have a logistic map taking the growth rate, the initial condition, and n like this. Okay, that should be talking about number of iterations. So we have X is X naught and all that and all that. So we have the map itself here and a logistic map, by the way. So for chaos, we have the logistic map with 4 as the growth rate and 0.3 as the initial condition, and we have 500 iterations. For random data, we just have np.random.rand, random data, 500 random data points, basically, you know. And with that in place now, we just want to check. We see the deterministic chaos and the random noise. So they may look alike, but the deterministic chaos still follows a kind of pattern. So look at it. Both of them look alike, but this one still follows pattern, while this doesn't follow a pattern like that. Okay. So we tried to make sure that both of them are both 500 steps. Okay. So we have the same 500 steps. This is deterministic chaos and this is random noise. While deterministic chaos may look like random noise, it is not because it is deterministic. It still follows a rule. So we go for universality in dynamics. So different systems often show the same patterns. We have examples in population models, fluid turbulence, lasers, and economics. Many follow the same routes to chaos. So for the period doubling route, for instance, as parameter R increases, so stability becomes period two becomes period four becomes period eight, and before you know it, it descends into chaos. So this sequence appears in many systems. So a system starts out stable, and then you have period doubling, further period doubling until you get into a chaotic state. And then we talk about the Feigenbaum scaling, which you had seen before. The ratio of bifurcation intervals converges to delta, which is approximately 4.669. So this value is universal for many systems. That's the Feigenbaum scaling. Okay, so we have the bifurcation diagram here now. So we still use the logistic map. Then R is, so we take R between 2.5 and 4.0. So you can see the evolution of the system, probably from a stable state until it descends into chaos, courtesy of period doubling, right? So see this, see what happens here now. Okay, this is the first. Okay, yeah, this is on the first. Okay, now this is it here. So between 2.5 and 4.0, see what's happening. We have stability, and then we have period. What's that thing called now? We have period two, yeah. So we have stability right here at this leg. You have stability right here. If you cut this off, it looks like but what's that thing called? A fork something chaos bifurcation, yeah, it's pitchfork bifurcation exactly. So from this stability to the uh, period 2. Then you go to period 4, period 8, and then it descends into chaos. So stability, period 2, period 4, these two wings, period 8, 1, 1, 2, 3, 4, 5, 6, 7, 8, and before you know it, it descends into chaos. So that's some universality in dynamics, right? Different systems often show the same patterns. So you have period doubling root, for instance, and that's how it goes. As it goes from stability to period 2, period 4, period 8, and chaos ultimately. Okay, so some open problems in dynamical systems will be things about turbulence, how chaotic flows organize, climate predictability, limits of long-term climate models. Then you have high dimensional chaos, like in brain and network dynamics. Then from you have quantum chaos, classical chaos in quantum systems, and you have control of chaos, stabilizing chaotic motion. I think we did some things about, there was a particular instance where we tried to stabilize a Lorentz system, which is a climate kind of model, and we're able to introduce a control variable on the x variable, and we're able to, so by tweaking that control parameter, we could actually put the system under check somewhat. Okay, we have an example here, by the way. So chaos control. So you want to apply small feedback to stabilize motion. The modified map, with the normal map we know is x sub n plus 1 into rxn into 1 minus xn. But now we have this control part. Now this small feedback for chaos control, which is minus k into xn minus x star. So this k now is the parameter for the control. So we can visualize this in this code, for instance. So we have of course, you're using matplotlib, a defined controlled logistic. And so the parameter growth rate R, you have X, the variable, and then the target is 0.5 and K is 0.2. So the new logistic map is now Rx to 1 minus X minus K into X minus target, like that. So you can then return maximum 0.0, minimum 10, comma X new, and clamp to 0, comma 1. So you have the parameters R 4.0, which is supposed to be chaotic, as we know. X naught is 0.2, K is 0.2, N is 200, that's number of iterations, and K now is the control parameter, if you like, and then you try doing all the plots. So you plot the values, you have the control logistic for everything in control logistic, you have X values and you keep appending, and then we see the stabilized chaos control, and we see the number of iterations and all that. So this is what happens right here. So at the end of the day, we have the stabilized control somewhere around here. But you have the system that is normally chaotic, but then the stabilized control comes somewhere in the center here around 0.5, which is the goal we're aiming for, to stabilize that. So what if we increase the control parameter? What happens to the system? Okay, I mean, you can see the system is finite. It's not as crazy as it was initially. So let's make it smaller then, like 0.02, you know, like this. Okay, 0.02. Yeah, so you see what the kind of thing here. So it's not as organized as it was before. So make it go further. So it's more like, as we have, okay, let me do very, very small and see what happens. So as the control becomes smaller, the chaos increases, right? So let me see very large control, like say 200. Is that, yeah, so you see, the more you tighten it, the more the the chaos becomes a bit more organized, you know. So that's the kind of thing we have going on there. Okay, so let's take it back to what it was. 0.2, and then we have this kind of stabilization in the system. All right, so having talked about that, let's talk about some learning pathways in dynamical systems. So that's some step by step. If you are really interested in dynamical systems, you want to check. First of all, you have learning proceeds in stages. In stage one, you can look at the foundations, talking about calculus, linear algebra, and differential equations. And I have all of that on my channel. So as usual, just go here and then try to go to my channel right here, like this, and then you check on playlists, So for playlist now, everything I'm going to mention here, you can find them. Anyone that is not there, I should make it happen anytime soon. So we talk about calculus, linear algebra, and differential equations. I have all of that. One of my earliest playlists is calculus. I think that was my second playlist after matrices. So it was calculus. So I have matrices here. Yeah, basic calculus, 26 videos. Then the next thing is linear algebra. That's one of my latest playlists, linear algebra. This 43 videos here. Then differential equations, of course, I have 87 videos covering differential equations. Okay, yeah, here. But if you want to see them separately, Laplace transform is part of that. Partial differential equation is part of that. Ordinary differential equations is also part of that. So I split them up in case you want to look at them separately. But everything is aggregated together under differential equations, 87 videos. Okay. Then we have nonlinear systems, phase space, stability, and limit cycles. Of course, you can look at that under this current playlist on dynamical system. That's the latest playlist I have going on. So with two more videos, I'm going to have 19 videos in total, and then it will come to an end. Of course, I also have other instances where I've talked about things like limit cycles, phase spaces, and everything. If possible, I'm going to talk about mathematical biology somewhere along the line. Then we also have chaos theory, where we talked about attractors, like exponents, and fractals. That's still under the current playlist. Then you can have advanced topics like ergodic theory, PDE dynamics, and networks. So you can check for for ergodic theory, it's under this dynamical systems playlist. For what else do we have there? We have PDE dynamics. So you can check the partial differential equations playlist to see. They also come with Python codes to drive home the point making in each of the videos. So these partial differential equations. So if you click on it, you see that um, there are also videos on partial differential equations, right? So you see some numerical approaches to some of these things. Okay. Then, with that in place too, we then talk about networks. Of course, I have a playlist on network theory, network graph and network theory, I believe. It's somewhere close by. Graph and network theory. Yeah. So this graph and network theory right here. And then we move on to okay, some applications, right, of all these things. So, I mean, we've seen ample applications in biology, for instance, where we talked about um, uh, pre-predator model, epidemiology. In physics, also, we've seen things like the what's that thing called now? Van der Pol oscillator or something like that. Van der Pol limit cycles, yeah. And we've seen it in, I mean, we talk about economics too, when you talk about stock prices fluctuating a lot. Then, of course, in AI, and of course in neuroscience, because you've seen some models that are related to this in neuro to dynamical systems in neuroscience. So we have a simple example where you just have a model that whose result is e raised by minus x. That's dx is equals minus x, basically. So just for demonstration, we've done that a lot previously. We also did numerical method where we solved some of these things with with Euler's method and of course Range-Distributor, where we saw Range-Distributor having better results for the most part, in all these instances. So these are things we had considered, and you want to keep checking them out to see how these things play out all the time. Okay, so with that in place, we move on to Lyapunov exponent. So I mean, we've come across Lyapunov exponents. The first time we saw it was when we talked about chaos, especially when we talked about quantifying chaos. Lyapunov exponents came up, and we keep saying this formula over and over again. And so Lyapunov exponent measures sensitivity to initial conditions, right? And the definition is the average definition. The definition in terms of average, right? That's lambda is limit as n goes to infinity of 1 over n summation of ln of f prime of xn. So if lambda is greater than 0, that's chaos. If lambda is less than 0, that is stability. Okay. So with that in place, we then have, we can compute the Lyapunov exponent for a logistic map. That's about the most talked about model we've talked about. The logistic map is the most important, the most common model we've talked about so far in this whole playlist. So we have it coming up once more here. So, yeah. So you have Lyapunov with parameter R, that's the growth rate, X naught initial condition, N number of iterations. So X is X naught, S is zero, and for everything in the range. So for this now, we keep updating this S now, plus or minus log ABS because of the definition, right? This particular part. So because summation of this now. So because of that summation, we keep updating that particular part of the system. And then of course we can run this and then we see what that looks like. So it gives us Lyapunov exponent of 0.69. So it tells us because this lambda now is greater than zero, we are going to have it talks about a chaotic system for sure. Like it, of course, it is important because R is 4, it has to be chaotic. If you still have an R like say R is 2, we still have it under control, not so chaotic yet. Aha, so you see negative infinity. So maybe I should just say 2.5 even. So for the 2.5, we have minus 0.693. So that's negative value. That means for so I mean this is an indicator, right? For 2.5, this system is still not chaotic. It's stable, right? It shows stability. So in fact, we can keep increasing it by zero point 0.5. If what if we go to 3? Is it chaotic or stable? So at 3, it is still chaotic, but you can see it's decreasing. It's going possibly getting closer and closer to positive values. So what if it's 3.5? Okay, it's still not chaotic, it's still stable. So what if we go to 3? Let me go step by step. 3.6. Now at 3.6, it's already chaotic. So let me try 3.55 even. So I want to move as close as possible. What about 3.56? 3.56. It's still not still stable, but it's moving towards chaos gradually. Then 3.58, 3.58. Okay, and now it's getting chaotic like that. So from 3.6 upwards, you can be sure the system is definitely chaotic. So like that, so we can see that there. So here now, we then have final synthesis. So we talk about determinism. That means rules exist, right? Then we talk about predictability. That's limited. And then structure, you can have hidden order. Then randomness talks about true uncertainty and universality. That's you have shared patterns for different systems. For open problems, you have many unsolved problems you want to pay attention to. And then for learning is progressive. So you go step by step from the smallest to the biggest ideas. And my channel provides you the opportunity to build gradually to become an expert in dynamical systems. So central idea, simple rules can generate complex behavior. That's the central idea of complex system. Simple rules can generate complex behaviors. We see this in fractals, we see this in chaos theory and all of that. So dynamical systems unify order and chaos, mathematics and nature, theory and applications, because we see uh, fractals in plants and animals and all the kind of pattern formation. You have very simple pattern repeated plenty times. Then you have fractals which border on chaos. So you have theory and applications coming together. So we have practice problems as usual to drive home the point we've been trying to make since this video started. 19 videos before now, or 18 videos. That is, so this is the 19th and the final, except something else comes up and I have to make another video. So solve the following problems, show all steps you appropriate, consider the logistics, and find all fixed points. So you just, to find fixed point for this kind of discrete thing, is just freeze all the x's. So you have x equal x star equals rx star into 1 minus x star. So solve for x there, you get all the fixed point. Then you determine their stability, and that's absolute value of is it x or something like that? You determine less than one, that's stable, greater than one, unstable. And for stability analysis here, you can, given the discrete system, find the fixed points. You do the same, x equals 0.6, x plus 0.2, and you solve for x and all that. Then you can do the cobwebbing thing here, cobweb diagram. Then continuous system, you have a continuous system here. You find all equilibrium points equate to zero, right? Phase plane analysis, you can try that here too. So it's clear that y is zero here, and because y is zero, you can put the zero here to an x. Okay, y is zero, right? Y is equal to zero, and this is also zero. So you can get some values for x here. So you have zero against zero and other values that you might be able to get here. Then you have 5 and 6, sensitivity dependence. Check, work out all of that. 7 and 8, you have noise effects here. And of course, 9 and 10, you have chaos control. And then you can even try out this application project. It will be good for you, especially if you're interested in linear dynamical systems. So you can choose one real world system like a population model, population growth, epidemic spread, neural activity, economic analysis, and formulate a dynamic model, analyze equilibria, study stability, simulate numerical and interpret results. That can be of help to you. I mean, if you're interested in doing this and if you get to do that, just you can let me know, reach me on any of the social media platforms, and I'll be able to respond to you. Okay. So with this, I come to the end of this interesting video talking about conceptual synthesis in dynamical of the idea of dynamical systems, and of course, the last video probably in the whole playlist for dynamical systems, except something else comes up, like I keep saying. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, question, what are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you membership with special privileges, like some videos are meant for only you. Some videos you get to see them before others see them. You can ask for my PDF copies of my notes. We can hang out together, you know. I can organize private sessions for you as a member of the channel. And ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on. Until I come your way again, keep doing maths right. I think the next playlist I may want to do will be something like indices and logarithm. That's more of bothering on high school stuff. So I think the high school people too need some things here. All right. So if you have people in high school, they can have things here to learn. Of course, if you also have ideas about playlists I should make that I've not made already, just let me know. I might be able to pull that off. I also have ahead of I have in the pipeline, maybe at some point, maybe talking about the history of mathematics or something. Maybe that may be interesting to some people. So if you think that you're interested in the history of maths, just let me have a comment either on Facebook or on YouTube or anywhere else you can find me. Okay. Um, Again, don't forget to comment, like, and share so that more people can have access to the great content I have going on. Until I come your way again, keep doing maths right. Bye.